I'm Carl, and I'll be your second instructor for this course. In this chapter, we'll discuss the 4 types of analytics, starting with the basis, descriptive analytics. In this overview, you can see the 4 main types of analytics: descriptive, diagnostic, predictive, and prescriptive analytics. Each type of analytics has its own main focus. The more we go to the right, towards prescriptive analytics, the more advanced questions we can answer. However, this does not mean that the most advanced analytics types are always the best choice. For instance, choosing prescriptive analytics when descriptive analytics would suffice needlessly complicates the analysis and increases the time it takes. The suitable type of analytics depends on the question we want to solve. In the case of descriptive analytics, the leading question is, what is happening? Descriptive analytics focuses on summarizing and visualizing the data. This type of analytics can be used to get to know the data based on its variables. Variables are the characteristics of interest we have measured or observed. For example, temperature in a weather dataset. Descriptive analytics can also be used to investigate relationships or patterns in the data. For example, whether specific groupings occur or one variable is closely related to another. Lastly, descriptive analytics can be used as a preparation step for more advanced techniques like building a model. In its most basic form, descriptive analytics consists of the calculation of descriptive statistics, like averages and maximum or minimum values of variables. These help us answer questions like, what is the most common value? Or how spread out are the values? Visualizing the data is also helpful to get to know the characteristics of the data, in particular to see patterns, groupings, or other relationships in the data. Outlier detection helps to find values that are very different from the majority, which can help to find errors. A more advanced and comprehensive form of descriptive analytics is exploratory data analysis, or EDA. The focus of exploratory data analysis, as the name implies, lies in exploring the data, assessing its main characteristics, finding relationships, patterns, or groups, and suggesting hypotheses for future analysis. Often, it is contrasted with hypothesis testing, which is more formal and specific, while EDA looks at data in a broad, open way to discover something that is not known yet. It combines different techniques to gain a comprehensive picture of the data, including basic descriptives and more advanced techniques such as cluster analysis to find groupings. It also places a strong emphasis on visualization to gain additional insight. It can be used as preparation for further analysis and offer valuable insights on its own, for example, to discover data problems. Suppose you work for an ice cream company and are tasked with analyzing ice cream sales. You are particularly interested in which flavor sells best. Using descriptive analytics, you could count the number of sales per flavor and, if needed, separate the numbers per store or month. The insights gained from this can then be used to limit the number of flavors to the most popular or select new flavors to sell based on the characteristics of the already popular flavors. Now that you have learned about descriptive analytics, let's put that knowledge into practice. In this video, we move on to the second type of analytics, diagnostic analytics. Just like a doctor diagnosing a patient to find the underlying disease, diagnostic analytics aims to find the root causes of events. It is similar to descriptive analytics, but focuses more specifically on the why question. Diagnostic analytics can be used to find potential causes of events or reasons for behaviors, investigate causal relationships, and, most importantly, the results of a diagnostic analysis can be used to suggest solutions based on the identified causes. While diagnostic analysis can provide evidence for possible causes, it can be tough to prove that there is an actual causal relationship. This is because a statistical relationship between variables can be caused by a third factor we don't know yet, or even by coincidence. This is why domain knowledge is a crucial asset in diagnostic analytics to help assess whether the results are plausible. Additional analysis and setting up experiments can also help strengthen the case for causality. A common technique for diagnostic analytics is drill-down analysis, which consists of moving from general summary data to examining underlying data. For instance, from a sales report showing rapid revenue growth and digging deeper to identify the stores and products that contributed most to the increase. Other common techniques include correlation and regression analysis, which can tell us if variables are closely related. Hypothesis testing, when the probable causes are theorized beforehand, and root cause analysis, which we'll discuss further in the next slide. Some of these techniques use similar methods to descriptive analytics, and you will often see similar descriptive statistics and visualizations. The difference is that diagnostic analysis is more directed at underlying causes, while descriptive analytics offers a broader view of an event. Root cause analysis, or RCA, is a formal set of steps used to look beyond superficial causes that have a direct effect, named contributing factors, by investigating these factors further to identify their causes. This drill-down process continues until the root causes are identified. How far this process goes is typically determined by domain knowledge. An RCA process consists of 5 steps. First, define the specific event under consideration. Second, collect all relevant data related to this event. Third, determine contributing factors based on analysis of the data. Fourth, drill down to root causes. Finally, recommend solutions based on the identified root causes. Suppose you're working for an airline and are tasked with determining why the customer satisfaction rate is declining. Using diagnostic analytics, you could identify some potential causes by finding and grouping keywords in complaints and ranking the most common categories. You could also investigate connections between the complaint categories and other data you might have, like waiting times or delays. This is typically based on domain knowledge. The results of this analysis can then be used to suggest potential solutions for the most common categories of complaints. Now that you know all about diagnostic analytics, let's practice. After learning all about descriptive and diagnostic analytics, it is time to take a closer look at predictive analytics. Descriptive and diagnostic analytics are concerned with the past, or at most the present. Predictive and prescriptive analytics look at the future. Predictive analytics are focused on identifying outcomes and their probability, helping us investigate what will most likely happen based on what we know from the data. Predictive analytics can assist in anticipating the most likely outcomes of an event, like predicting whether a machine will soon fail based on maintenance data so that the company can organize repairs in advance. It is also often used to forecast how a specific trend will continue. For example, to predict stock prices or the evolution of a pandemic. Often linked to future events, predictive analytics can also be used to predict something that is not yet known in the present. For example, based on symptoms, predict which disease a patient most likely has, or, based on the characteristics of a transaction, predict whether it is fraudulent or not. Either way, predictions are always associated with a degree of uncertainty, even more so if we look further away from the data we have. One of the most common techniques used in predictive analytics is machine learning, a set of techniques where computers learn from existing patterns in data to make predictions on new data. A distinction can be made between classification and regression. Classification predicts categories or membership to a group, like predicting whether a customer will cancel their subscription in the near future. In contrast, regression predicts values, such as predicting housing prices based on the characteristics of a neighborhood. Time series forecasting focuses on predicting future values over time, like predicting sales revenue for the next quarter. Predictive text analytics is a subgroup of predictive techniques focused on text, typically used to predict which category a text belongs. For example, whether an email is spam or not. Regardless of the technique used, there are some common steps all predictive models use, which we'll discuss in more detail on the following slide. The first step consists of defining what we want to predict. Second, collect and prepare the data related to what we want to predict. Typically, the data is split into a training set for building the model and a smaller test set for evaluation. The data is then used in the third step to build and train the model until it provides accurate predictions on the training data. When the model is ready, the predictions are interpreted and evaluated on the test data using predetermined metrics like accuracy, which is the percentage of correct predictions. Usually, multiple metrics are used to evaluate a predictive model thoroughly. Finally, the model can be further fine-tuned if necessary. Before any great sports event, many try to predict who the eventual winner will be, from animals with predictive ability to supercomputers. The computer models use data like team ratings, player ratings, current rankings, estimated difficulty of the matches, and so on to predict who will most likely win and other things, like how likely a team will reach a knockout phase or the chances of getting to the final. Time to put your knowledge of predictive analytics into practice. Now that you have learned about descriptive, diagnostic, and predictive analytics, it is time to learn about the fourth type of analytics, prescriptive analytics. Prescriptive analytics builds on the results of predictive analytics. While predictive analytics allows us to identify potential outcomes and their probabilities, prescriptive analytics aims to take this further and take action on the predicted outcome. As can be deduced from the name, with prescriptive analytics, we are trying to answer the question, what is the prescribed or recommended course of action? And, by doing so, select the best action given the outcome we want to achieve and taking into account related benefits and drawbacks. The primary purpose of prescriptive analytics is to help us decide what best to do. In doing so, it provides the following benefits: the ability to make informed, data-driven decisions, optimization of processes, and mitigation of risks associated with particular outcomes. Common techniques used in prescriptive analytics include rule-based systems, which consist of generating a set of rules or decision logic to get to the best outcome. These rules are generated by domain knowledge, a machine learning model, or a combination of both. In reinforcement learning, an algorithm learns to achieve a particular objective or optimize an outcome by receiving positive and negative feedback when running through a set of actions. Scenario analysis and simulation consist of running through a set of predetermined scenarios or simulating multiple outcomes to help select a decision that leads to the best outcome. And lastly, the recommendation engine is one of the most well-known techniques. We'll discuss this further in detail on the next slide. You've probably seen this a lot when shopping online or watching a movie on Netflix. You're recommended what to buy or watch next. Behind these recommendations is a recommendation engine. It first looks at the products you viewed or purchased in the past and uses this as data to predict what other products you would be interested in purchasing. Then it provides specific recommendations based on those predicted interests. Suppose you work in a bank and transactions on a particular account have been flagged as possibly fraudulent. How should we proceed? Block the account? Call the customer to double-check the transactions? Have a fraud analyst do a manual check? Each of these options comes with its risks and benefits. We want to avoid fraud losses, but we would also like to avoid the negative impact of completely blocking a client's account. It is also possible we have limited resources. For example, the fraud analyst can only check a limited number of cases daily. Prescriptive analytics can assist in these kinds of considerations and decisions. Now that you've learned about prescriptive analytics, let's put that knowledge into practice.